Hi, I'm Stefan. I think a lot of you know me, but I'm presenting a talk today on LLMs for hardware design. This is more presentation of like it's like a combination of like what I'm working on and kind of like an overview of what the field looks like because this is a very kind of new and emerging topic. Um, so I'm just going to go over a brief like history since it's like you can put all of it on one slide basically. So looking at LLMs, back in the day we had people thought the more data we can just train bigger models with more data, right? And we get better scaling. And then we started adding stuff on top of it like RAG and tool usage, and tool feedback, and like guided decoding. And this is kind of like when OpenAI was like the only big LLM player in the field. Um, then kind of like in the middle after that, we had like open source models that were just as big and just as good, like Llama. And we also had a lot of smaller open source models being released that were also very high performance. Oh, back. Oh. And then now today we have more complicated integrations into the LMs like multi-agent systems. And we have this like very new stuff like the inference time compute scaling and this like new idea of like reasoning, quote unquote, however you want to interpret that. And then now we also have like a new set of language models that are also open source and that also are integrating all these new like ideas. So looking at the LLM for hardware design, the very first thing that people did were like, let's just take ChatGPT and ask it to make like Verilog modules, like something really basic, right? Just code gen. And NVIDIA kind of took this like one step further, and they're like, okay, we'll train it on all our customer data, all our Verilog, all our scripts, and then we'll just tell everybody that it's like really good. So they did that. And then eventually in the academic community, we have these open source like benchmarks for Verilog design using LLMs, and I'll talk about those. People started like integrating like the tool feedback, like any errors the EDA tool might give you because the design was incorrect, they'll feed it back into the LLM to correct. And people started also looking at LLMs for HLS code generation, which is something I'm working on. And then alongside, people are working on like generating test benches and assertions, and people are working on like scripting EDA tools with LLMs. And now we also have people working on like, when you design a module, you design it hierarchically. So can the LLM also do that? Can we have better focus, like better data sets that are tuned to this kind of problem for LLM for hardware design, right? So this is kind of like, I guess what you could encompass everything that's kind of going on in the field right now. And then these are all kind of like the workshops and where you might find a lot of these papers related to this topic and conferences as well. So what is like a benchmark look like? Like what does this kind of look like? So VerilogEval, I'll show you an example. You have a prompt. It's like make this module that has these inputs and outputs, and then it describes like what the functionality of the module should be. Then you pass that into an LLM and it generates some kind of generated module. And then the benchmark has a reference design which is known to be correct. And then they have a test bench which they also provide. And basically what they'll do is they'll like compile the Verilog and then run simulation, and they'll compare the they'll like send stimulus to the designs, and they'll compare the outputs to see if they're the same, right? And if they're the same, then it passes the functionality check as well. But there are several limitations. First, VerilogEval are like really easy problems. They're from this like educational resource online for like learning digital design, and they're also one module designs, and they're like very small and trivial. You need a reference design. So like in the real world, like nobody gives you the reference design ahead of time, right? Then you don't have to make the design. So that's still a problem to solve. And also you need a test bench. Like in the real world, like you also don't just get that for free. Also, their code is broken. I've like, a lot of these benchmarks are broken, as you'll see, but there's still issues trying to reproduce this work. It requires, it's just a non-trivial amount of effort to reproduce. There's another benchmark like called RTLLM. It's basically the same thing where they have like the reference and the test bench, and you generate the design and you compare against that. They go one step further. So like if it passes simulation, you can also collect like PPA metrics or quality of results metrics and kind of study that. They have the same limitations, and the test benches are even more broken. I wasn't able to reproduce this benchmark at all. It was very annoying. So there's a lot of also other limitations, like people don't know how to calculate like pass rates correctly. Like the prompting format of like how the code should be like, should the code have like be included in tags or like markdown? This all very haphazard. And then people also, for some reason, don't include, all the key details needed to gather like one-to-one comparison results for these hardware benchmarks. And they're also very buggy. And normally I would like, this is like, this happens all the time, but these are like benchmark papers. So the whole point is that they should be reproducible. And that people going forward in the hardware community, like we shouldn't be very loosey-goosey about these kind of benchmarks. There's other people working on different things. Like people are using, so there's like in Python, people have written DSLs. So you can like write Python and then that gets translated into like Verilog. And those are kind of slick. So people use LLMs to generate the Python DSL that will eventually get converted to hardware. And there's benchmarks for that. And there's also people working on designing like hierarchically. Can we like benchmark how well LLM can generate like a hierarchical design? So what does like a canonical like flow for like LLM aided design look like? So typically you might have a natural language description and a test bench provided from the user. The LLM will generate the hardware implementation, and then you'll run through different tools like compile, simulation, and synthesis or implementation. And you could fail to like parse out the code from the LLM. You can fail to compile. Like there could be syntax errors. There could be simulation errors, and you can also fail synthesis and implementation. So, and if you pass, you get like simulation results and QRR metrics, right? So the idea is that like we can use tool feedback. We can take these errors and feed them back into the LLM at every stage to then make corrections to the design. We can also compute like pass rates at every stage of the design as well. And we can use different tools. So like, for example, you can use open source tools to run all these kind of different stages and also like commercial tools. But if you use open source tools, the feedback loop is very fast. Like it takes tens of seconds to run the compile simulation and synthesis for like the very small like VerilogEval. So this is quite quick. And with the tool feedback, it makes that very efficient. So looking at HLS, HLS is more complicated. You now have like C simulation, synthesis, co-simulation, and then implementation. And it's much slower. It can take from minutes to tens of minutes to like go through the flow just to get some error and then have it regenerate an answer, right? So typically the compile and CSIM step is still slow because the template libraries that HLS provides are bad. Vitis HLS can take 30 seconds to several minutes depending on the design. And then all of that afterwards, the RTL simulation and the implementation can take much longer. And even we have some tools in our lab to speed up simulation, but clearly every other stage in this flow is very slow. So this feedback loop is kind of pointless. The person might like generate this module, it generates the source code, and then you wait minutes for it to make an error and then go back into the LLM. So this is kind of, in a sense, there's some hurdles here to actually using tool feedback efficiently. So what I'm working on, so basically we have no idea of, we don't have a VerilogEval or RTLLM for HLS designs in the community. So I've been working on assembling kind of these things like Polybench, MaxSuite, CHStone. These are like traditional benchmarks, but turning them into LLM benchmarks by adding natural language descriptions, like consistently formatted test benches and stuff like that. But most importantly, writing all the tooling needed to integrate the LLMs with the HLS tools in like a clean and easy to use API. And this is very non-trivial. I've worked on this for like 8 months, and there's a lot of gotchas in between. So doing this correctly and cleanly and in a modular way is actually very complicated. And in this case, we don't even worry about co-simulation or implementation. We're only looking at the first 3 stages of the design flow. But that can still be very long because of HLS synthesis. One other thing that I'm looking at right now is that rather than just generating HLS code, let's say someone wrote some unoptimal, C code or HLS code, and we want to have the LLM make edits to the code to actually make it more HLS friendly or more HLS optimized, right? So like converting floating point types to fixed point types, or doing like refactoring to add Pragma HLS pipeline, or refactoring to use streams and data flow, all this kind of edits. And we have some very, very, very initial results. So for example, the easiest case would be like a 0-shot evaluation. Just generate, edit this code so that it uses fixed point types instead of floating point types. This should be easy and very local. You're not doing like structural refactoring to the code or anything. But even then, they immediately go straight. So the pass rate after just compiling the code is only 50%. Just like running the C code through Clang after you've made the edit. So there's still some issues here. And we might expect that if we add tool feedback, like it should go up. But for some reason, we see the pass rate go down. And we do not know why that is the case yet. There's like a very small chance that it's a bug, but at this point, we've ruled out a lot of different things that might indicate that this is actually a much more difficult to do for now, based on our best hypothesis. One thing that we can maybe propose is that we can have ML models integrated into this feedback loop to say predict, post HLS synthesis, latency and resource usage without having to run HLS synthesis, right? So we can collect data, train this model, and then do that. We can do the same thing for like post-implementation QOR, and we can also use very fast simulation. So what we can actually do is integrate the results from synthesis, the QOR results from synthesis and implementation. We have the second feedback loop to actually optimize the performance of the kernel, once it can actually compile or go all the way through. So this also brings us to like another problem that I'm exploring at the moment is like, what is a good HLS benchmark, right? So the idea is that like a good HLS benchmark design is one that scales well with the amount of effort or resources used, right? The more pragma unroll that I do or array partition that I do, the lower the latency should be, right? And so the idea is that we started running a lot of large-scale experiments to synthesize HLS designs across all different kind of configurations and clock speeds and device family to see if we can find, these designs scale well with the resources and these ones don't. And to do this, we're using our previous work, HLS Factory, to kind of collect this data. And what we see is that some designs correlate. So on the y-axis is latency, and on the x-axis is resource usage. So we should see the line go down, right? So the more resources we use, the higher parallelism, the lower the latency should be. But in reality, the correlation here is still not very clear. And these are very interesting preliminary results that we're still collecting more data for and trying to model better. Yeah. And we can also look at, like a worst negative slack versus resource usage and across different designs and stuff like this. But I won't go too much into this. So the end goal here, to tie it into the LLM stuff, is that we're going to try to use the LLMs to characterize or generate good HLS benchmarks to actually scale well, right? We can then use these benchmarks to profile like FPGA fabrics and architectures. And because the more optimization and resources used, the better they scale, they act more like practical end user designs that Xilinx and AMD might be interested in looking at. And then finally, I want to talk about inference scaling for LLMs. So the idea here is that if you have a problem with a verifier, so in this case, like we have a compiler and we have like a simulation tool, we can generate many different samples of the same Verilog design from the LLM. So given one prompt, we can generate like 100 different random possible candidates for the solution. And as long as one of them passes like the Verilog syntax and the simulation, then you win, right? You just need one design to work, and then you've solved that one specific design problem, right? So it turns out like if you just generate more and more samples, the likelihood that like one of the designs will be correct for your given prompt goes up. It's like really dumb. You just keep sampling the LLM, but it actually works. And you can basically get state of the art on VerilogEval with like very small open source models that don't require any fine tuning, just by generating more and more possible solutions for like any given prompt. And that's what this is showing here. Each one is a different LLM, and we generate from 1 to 100 samples. And at the 100 samples, the open source model can actually beat GPT-4 on VerilogEval. And what's interesting is that you get like huge gains just by doing this repeated sampling. So the blue is just like the base performance if you just generate one design, and the green shows you the increase if you generate 100 designs per prompt. So you can see it's pretty significant. And what's really interesting is that like if you look at individual problems in the benchmark, they all scale differently. So there's a set of problems that are really easy that are all solved like within 100 samples, but then there's another subset of designs in VerilogEval that are never solved on any of the samples, right? So this kind of indicates that in VerilogEval, there's like a group of like really easy problems and a group of really hard problems. And I guess is not very characterized anywhere, but it could kind of be important to know that this benchmark is structured like this to like improve it in the future. So there's a lot of interesting ideas with this inference scaling. Like can we just do this thing for HLS? If we add the tool feedback, does the performance boost is the performance boost even bigger? And can we actually do partial design scoring? So like as we generate the design line by line, can we say like, oh, this design is actually like not a good candidate to keep going? We'll throw it away and we'll go down this different path, right? So there's all these people, and this all is happening in parallel in the LLM community now. They're working on kind of related things for inference scaling. So yeah, that's what yeah. And then so the final thing I wanted to point out is that if you're interested in looking at like what people are doing like right now, or can extrapolate what labs are working on this kind of problem, you can look at MLCAD, and there's this new kind of conference that was a workshop last year for LLM aided kind of hardware design. And so this is where I would kind of look at like the most recent work that is like officially published in conferences. Yeah, and that's all I have to talk about today. So thank you.
LLM, can you just start from regular source code instead of HLS code?
Yeah, so people have basically there's actually some people working on where like they assume that somebody has written just some like C code that might not be synthesizable, and the whole goal is to turn it into just make it synthesizable, right? So that's like one problem versus generating from scratch, like just generate the HLS kernel from natural language description versus just making edits, assuming the design is already synthesizable. So they're all like different sub like problems that you could choose to tackle with the LLM. Yeah.
I have two questions. First one, a little cheeky, but does this definition of hardware design include analog or mixed signal designs?
So there are people who are working on that. I don't work on that. So there was people working on like I think the like Spice, like people working with like Spice net lists and generate LLMs for that, and people also working on I think it's like the analog version of Verilog. I forgot.
Verilog,
yeah.
Do you have any names?
No, but if you look at like the
conferences,
the workshop, like the LLM aided design workshop from last year, there's some papers on that, and I think also at MLCAD.
That's fair. Thank you. But the second question is, I know I believe you had a benchmark collection, but for the verify step, right? Even though you can get one correct output, did you ever consider like collecting the correct verified outputs and then store them somewhere as, like reasoning traces that can either be contributed back to some type of,
Oh, okay.
repository or anything like that?
So in this approach, like this is just a small experiment I ran with the inference scaling. So what I do is I just say don't do any train of thought or anything, just generate the answers. So if you want, you could integrate some model that has like a reasoning trace and then use that and use it for like training and stuff. What you could also do is like replace reasoning by generating the design like line by line and then bailing if you think there's no hope in like continuing, like there's a better path. So it's they're like the same concept. Yeah.
No, absolutely. What I was saying specifically is this approach of, hey, generate 100 samples, right?
Yeah.
If one of them passes, I mean, I know you were collecting this at some point, which is like correct Verilog.
Yeah.
So I'm saying like, isn't this one way to generate?
Yeah. You can definitely generate traces like that if that's called output rewarding, where you take a trace, and if the output passes, then you consider that trace to be like a good trace.
Exactly.
Yeah. They have equivalent terminology for all this in the LLM world, but the same applies here. Yeah. Yes.
Yeah, I have a question related to maybe extending this work or related works.
Yeah.
A couple semesters ago, I was in a class related to hardware security, and one of the presentations was about using LLMs to generate HDL, so like some Verilog or whatever, and then also taking that and then using a chain of prompts to hide a backdoor in the code. Do you think that what you have here could be used to check for backdoored code? Or
so people also working on this where they basically this is like, can you inject like malicious Verilog, like a Trojan, into the design during any stage using like the LLM, or can you find it using an LLM? So people are working on this. My only concern with this idea is that the attack model is kind of like weird. Like you'll never have like when you're actually people have worked on like they can like take a LLM and kind of tweak it or like fine tune it a little bit to generate these like subtle bugs, right? So that's like one way to attack it. The other thing with like people using LMs to find Trojans in HDL is a little goofy because usually when you have like a circuit that you're trying to like detect a Trojan in, you don't have like the HDL like the designer wrote, right? You have it already as like a net list or something like this. So like at that point, like the LLMs are not designed to like read Verilog. That's just like flat net lists. And so you could possibly train an LLM to like do that, but then you might as well use like a traditional approach, like a graph neural network to like search for the Trojan. So like this attack model of like you have the original HDL and it has a Trojan in it and you're gonna go find it is not like realistic in my opinion.
Okay, so you're saying an LLM wouldn't be suited, but like a more graph-based approach.
Yeah, that's what people typically use.
Oh, okay.
That's what I've seen.
Yeah.
But it's like supply chain attacks and vulnerable. Like the LM can generate a lot of bugs, and then attacker can exploit that. So clearly, there's also a lot of work on like verification and like coverage testing and using LLMs and stuff like that.
Okay, that makes sense. Thank you.
The time constraint, if you have more questions, you can talk to Stefan later. Sorry about the pizza issue. So pizza arrived now, so you guys can grab a pizza, but it would be appreciated if you can grab it fast so that we can sharply start at 9. So feel free to grab the pizza first, and then we are going to continue at 1:05 with the next presenter, Sarah.